Hi guys, welcome back. In this session I'm going to talk to you about Boolean polynomials, and we'll see that because of idempotence these have some interesting properties. This will be a very short session covered in just a few slides. Let's start by talking about the exponent of a number, and we're talking now exponents in form of element x to the power of k, so k being the exponent. And exponents here, in this case, what we're going to talk about are elements of the set of natural numbers. So we're not going to talk about negative exponents, and we're not going to talk about exponents that are anything but natural numbers. Now, x to the k can be written in a different way using, if you haven't seen it before, this big pi looking symbol. The big pi simply means that whatever's to the right of it is multiplied k times. So x to the k is just x times x times x k times. And that can be written in that big pi notation. Now, in the Boolean case, we have something very similar. Remember that we said that the AND operation is Boolean multiplication. So we can use, in case that we are multiplying something multiple times, k times, we can use this big wedge notation. And it has essentially the same meaning as the big pi notation, but we're doing the AND operation k times in this case. You could, in fact, actually probably also use the big pi notation for Boolean numbers because Boolean multiplication is the AND operation, but we can do it either way depending on the notation that you prefer. And the advantage of the big wedge notation is that you are reminded of the fact that you're working with Boolean numbers. Now, there's something very interesting that's arising from idempotence that we talked about. Since Boolean variables are idempotent, and then using the associative property of the AND operation, remember x times x for Boolean numbers, or x and x, equals x. It's idempotent. So that also means that x times x, we can do either one of the x times x's first. They disappear because x times x is x. We can do this as many times as we like. So because of idempotence and the associative property, x to the k in Boolean numbers is simply x, and this is true for all Boolean numbers. So this is clearly not the case in natural numbers or real numbers, right? It would be if it was just the number 0 or 1, but in the Boolean numbers, for all numbers in the Boolean domain, x to the k simply equals x. So the exponent vanishes in Boolean algebra. And that has very important implications for Boolean polynomials, which we'll talk about next. Let's review really quickly what is a polynomial. You may not have seen one in a while, but I'm sure you have at some point in an algebra class somewhere. But a typical polynomial is written as follows. We have a0 times x to the power of 0 plus a1 times x to the power of 1 plus a2 times x squared, x to the power of 2, and so forth, up to the order of the polynomial. This is a polynomial in a single variable x, where the numbers a are coefficients. They are constants, constant coefficients on our variable to the power of x. Now, polynomials may be multiplied together. So polynomials in different variables may be multiplied together to form new polynomials. Let's do an example here. For example, we have the first polynomial is x plus 2x squared, and our second polynomial is y to the third power. And we multiply these together, and we get the new polynomial xy to the power of 3 plus 2x squared y to the power of 3. So therefore, in general, a polynomial is an expression consisting of variables, coefficients, which are constants, the operations of addition and multiplication and negation, and positive whole number exponents. Remember though that the exponents are just multiplication really, right? X squared is just x times x. With that in mind, we can talk about Boolean polynomials next. Now let's look at Boolean polynomials. A polynomial on the Boolean domain is the same definition as before. So we have an expression that consists of just multiplication, addition, and negation, or on the Boolean domain, these are the and, or, and not operations. Remember, on the Boolean domain, those are the basic three operations, and every other function or operation can be written in terms of those basic three. What that means is that every function on the Boolean domain, every function or operation on the Boolean domain can be written as a Boolean polynomial. So every expression is equivalent to a Boolean polynomial on a Boolean domain. Now, we also had that because of idempotence, positive whole number exponents disappear. So, for example, x to the power of 3x cubed is x and x and x, because of idempotence equals just x. And also, so the positive whole number exponents vanish. The other thing is because there are only two numbers in the Boolean domain, the number 0 and 1, coefficients effectively vanish as well, because a coefficient can only be 0 or 1. If it's 0, the whole term disappears, and if it's 1, the coefficient isn't needed, because 1 and the term, or 1 times our term, our Boolean term, just equals our term again. Now, let's do an example where we compare, for example, on real numbers, the polynomial 2x cubed. 2x cubed equals x cubed plus x cubed, or xxx plus xxx. Now, what happens if we switch to the Boolean domain here? We still have x times x times x plus x times x times x, but because of idempotence, this equals the third power disappears and we get x plus x, and that because idempotence of addition just equals x. So the term equivalent to 2x cubed on real numbers, although it's not exactly the same, but the equivalent term is just x. We'll wrap up with a brief summary of what we talked about. We showed that all Boolean functions are equivalent to Boolean polynomials, and we saw that because of idempotence in Boolean polynomials, things simplify significantly because all exponents and coefficients vanish.